Welcome. This is an introduction to IP version 6. Let's take a brief overview of IPv6. First off, IPv6 is a layer 3 protocol designed to replace the classic IP version 4 protocol, or otherwise referred to as IPv4. The primary improvement of IPv6 is a much larger address space. Other improvements include a more efficient header and several auto-configuration features, neighbor discovery, and a few other things that we'll discuss in this slide presentation. First off, IP version 4 replaces the layer 3 protocol known as IP in your typical networking stack. As you can see here, IPv4 operated at layer 3. IPv6 is a replacement for that protocol. IPv6 is a network layer protocol in the same way that IPv4 was. Other protocols at the other layers in the OSI model should work perfectly with IPv6, meaning transport layer and your data link layers should work just with IPv6 just as they worked with IP4. This is theoretical. I'm sure that as we come up with enhancements, improvements to IPv6, we'll discover shortcomings or difficulties with interaction between the protocols like we do with any protocol introduction. IP has been around forever, so there is some struggles that we're going to have. For example, some applications will only allow the input of IPv4 addresses. They may require an IP address and they will not support IPv6 address format. Some applications rely on ARP or IPv4 broadcasts or other IP version 4 specific protocols that come with IP version 4, such as ICMP Echo or something like that, in which embedded in the IP version 4 protocol stack is a requirement that is needed by a specific application or by a specific network, a network application or network protocol. IPv6 has a much larger address space than IPv4. IPv6 has a 128-bit address as opposed to IP version 4, which is a 32-bit address. Whereas IP version 4 had 4 billion in some addresses, IP version 6 has a lot of unique address capabilities, and you can see the exact number here in the slide. Because IP version 6 has so many possible addresses, we can do some things. We can be very liberal with the use of IP addresses, whereas in the past we've been restricted by the size of the address space. So IP address space is very big. This gives us more addresses, but it also allows us to use addresses in a way that we could never do before. For example, in subnetting, we no longer have to worry about the number of machines in the network. We just simply have to worry about the number of networks required. So no longer do we concern ourselves with how many IPs are needed per subnet. We simply assign everybody the same very large block. We also no longer need NAT. If you remember, network address translation was designed so that we could put a device in between our private network and our public network in order to reduce the exhaustion of public addresses. NAT is no longer required. Hosts can also automatically assign themselves. Because every computer has a MAC address, that MAC address can now be embedded in the IP version 6 address. So therefore, we can use the MAC address to auto-configure and auto-assign an IP address. This allows us to basically assign every machine their own unique IP address based on their MAC. The packet header in IP version 6 has also had significant improvement. For example, IP version 6 has fewer fields. Now, IP version 6 obviously adds a 128-bit address, which is greater than the 32-bit that was consumed by IP version 4. But IP version 6 removes fields that were unnecessary before, so the total gain in IP version 6 header space is not as much, considering the fact that we're removing a lot of additional headers that were in the IP version 4 header space. So an IP version 4 header could be between 20 and 60 bytes, but an IP version 4 header is always 40 bytes. So you can see we're not adding a lot to the network payload by going to IPv6. IP version 4 packets contain a checksum, whereas IP version 6 does not. See, IP version 6 relies on other protocols completely to do that feature. Optional IP version 6 are no longer tied to the header. Whereas IP version 4, you had all these optional header features that you had to have in there, whether you used them or not. IP version 6 doesn't require that. So IP version 6 can be much more efficient, or appear to be much more efficient, just simply because of header space and header room. However, one of the disadvantages we have with IP version 6 rolling out is most of the hardware, switches and routers that are out there, and even computers, were designed to optimize IP version 4. So until hardware manufacturers catch up and they design equipment that is also designed to optimize IP version 6, you won't see the improvement in overhead, improvement efficiency that we would normally get with a more efficient header. We have to wait for hardware vendors to catch up. IP version 6 also improves auto configuration dramatically. IP version 4 had a protocol called DHCP, Dynamic Host Configuration Protocol. IP version 6 also has that protocol. It's now called DHCP v6. This allows for a stateful auto configuration, much like DHCP did in IP version 4. IP version 6 also supports what we call Stateless Address Auto Configuration, or SLAAC, S-L-A-A-C. This provides for auto configuration to a node that is stateless, and we'll talk a little bit about more what that means here in a few minutes. So IP version 4 provided a very basic stateless auto configuration. If you remember, this was called APIPA, or Automatic Private IP Address Assignment. Basically, it assigned you an address out of the space 169.254. some address. But the problem is you couldn't access outside networks because you had no gateway. Addresses were dynamic, and they changed, or they had the ability to change. And people implemented APIPA differently depending on what vendor you were. So it was not very good. Well, SLAAC improves upon the stateless auto configuration in a significant way. And we'll take a look at the difference between DHCP v6 and SLAAC in subsequent slides. Before we do any of that, though, let's take a deeper look at the IP version 6 address format. Well, first off, the address format is 128 bits long. It's represented using all hexadecimal. The number would be just too long to represent it with binary. And so we basically represent it in hexadecimal, and we separate it into 8 blocks of 16-bit hexadecimal characters that are separated by colons. So as you can see here, this 2A03, 2A03, basically each one of those characters represents 4 bits for a total of 16 bits. So each represents 4, 4, 4, 4 for a total of 16 bits. We separate each of these 16-bit blocks by a colon. And so we basically have 8 of those. So you have 8 16-bit hex blocks in the IP version 6 address. But notice this document right here, these example IPv6 addresses I've given you. Notice they're different and the lengths are different. Well, if I have 8 blocks of 16-bit hex, how come they're not all the same length? Well, that's because we use shortcut notation. So we're going to talk about how to shorten the IP version 6 address to make it easier to write and easier to understand. Full IP version 6 addresses are really long. So to make them easy, we've abbreviated them in a couple of ways. First, leading zeros can be removed from any address. So if there's leading zeros, we can remove them. Second, a group of zeros can be compressed by using a double colon. And you can also combine both of these methods together to create a really short address. We're going to take a look at how leading zeros are removed. So let's take a look at how leading zeros are removed from an IPv6 address. Notice here, in my first example, 0001 colon can be reduced to just 1 colon. See, I've removed the leading zeros in that block. And same with the next one, 0012, I've removed the 2 zeros and it's now 12. Notice though that I cannot remove trailing zeros. I can only remove leading zeros. So for example, on 10000, that still is represented as 1000. You cannot remove those zeros like you can with leading zeros. So that's the first way that we can shorten an IPv6 address, is by removing leading zeros in each block. The next way is with zero compression. Zero compression is you can only do it once in an address. You cannot do it in multiple locations. So for one address, you can only do it in one place. So here I have an example. I have an IPv6 1234:5678:, then a bunch of zeros, and then I end with 2 blocks. Notice all of those zeros can be compressed to 2 colons in a row. I've now taken all those zeros. Now you may ask yourself, well, how would I know how many zeros are compressed? Well, I know that by the number of blocks that are available. So as you can see here, how many blocks do I normally have? 1, 2, 3, 4, 5, 6, 7, 8 blocks, right? So if I compress those zeros in the middle, I now have 1, 2, 3, 4 left over. So now I know that there must be 4 blocks of zeros in between those 2 colons. So that's how I can know how many zeros there are. So this is this is the same address complex. Now, you can only do this once. So for example, if I have an address like this one down below, I can compress this once, meaning I can compress this block of zeros in red, or I can compress the block of zeros in blue, but I cannot compress both of them. The reason why I can't compress both of them is I have no idea how many zeros are in each block. So you can only compress one block of zeros. So this last example here is a complete no-no. You cannot compress 2 blocks of zeros in an IPv6 address. Let's take it some real world example. So let's try with a real address. This is Wikipedia's IPv6 address. So let's take a look at that. Here is a compressed and leading zeros removed, right? So we've taken the leading zeros. So that's pretty much how you do it. So I'm removing now the compressed version. Notice that 0000, the leading zeros have been removed. Now here is removing it with the leading zeros removed. As you can see here, the 0001 becomes a 1. The 0000 becomes a 0. And here's the no compression, which is the full address. So all 4 of these examples are the same address. So this one down below is the full address. This is the one with with leading zeros removed, with no compression. Notice that 0001, right, is not compressed. I've just removed the leading zeros, whereas here is compressed. See, notice the 2 colons have removed those 3 blocks of zeros. You see that? So that's basically how that works. So these are all the same address. They're just written in a different way. So now that we understand what an IPv6 address is, so when you look at it, you're not so confused. You don't look at it and go, whoa, what is this FE80::1? You now know what that means. Hopefully now you can understand a little bit more about IPv6 addresses, types, and scopes. IPv6 is just like IPv4. Different types of addresses have different purposes. Like IPv4, IPv6 supports Unicast and Multicast address types. However, IPv6 does not support a broadcast address. It uses multicast groups to pretend like it's a broadcast, if you will. The reason why is broadcasts are just considered bad. Sending a packet out to just everybody is not good practice. So we use multicast groups to reduce the limit and the scope of a broadcast. So we no longer have broadcast with IPv6. So IPv6 also supports what is called an Anycast address. And we'll talk more about Anycast in a minute. IPv4 did kind of have the idea of Anycast, but nobody really used it. So IPv6 does take advantage of the concept of Anycast, and we'll talk about that momentarily. Let's first talk about Unicast, though, because it's important to understand the terms. So Unicast is basically node-to-node communication, just like we're used to in IPv4. So basically, you go from node to node, one machine to one machine, or point to point. Unlike IPv4, though, IPv6 enabled nodes will always have multiple unicast addresses, meaning an IPv6 host will have multiple IPv6 addresses, whereas an IPv4 machine could usually only have one unicast, or sometimes you could add a second, but it typically only had one unicast address. In IPv6, you can reach that machine by multiple addresses assigned to it. However, the IP version 6 addresses that get assigned to that machine have different scopes. So I'll have an address for one scope, and I'll have an address for another scope, and I may have an address for another scope. So our IP version 6 addresses get assigned to the machine based on the scopes that that machine requires. Let's take a next look at, so we looked at Unicast, let's look at Multicast. This works just the same way it did in IP version 4. One machine sends to a group of machines known as a multicast. And basically this is, there are several established, well-known multicast groups. And if we take advantage of those multicast groups, our multicast functionality of IPv6 will behave just like IP version 4 broadcasts did. Once again, multicast addresses are also divided into scopes. So just like a unicast address is divided into scopes, multicast addresses are divided into scopes as well. Finally, let's get to the last one, which is an IPv6 anycast. This is a special type of communication from node to node. And basically the concept is this. There are a group of machines that can respond to the anycast, but basically only one machine will respond. It's usually the one that is closest. So basically you send something out to a group of machines and anyone can respond. Usually the one that is considered closest via shorter path or the one that responds the fastest will be the one that responds. Okay? And so anycast addresses inherit the unicast address scopes. So anycasts are in the same scope types as unicast addresses are. But anycasts are used for special communications, which we'll talk about later. Let's just review just a couple of key points about address scopes. IP version 6 address scopes set limits on what those addresses can communicate with. So if you have a scope that is central to, is scoped for only like a local area, then you're only able to communicate with that address in the local area. Whereas you might have a scope that is global, so you can use that address to communicate with a global scope. So each scope limits what you can talk to. An IP version 6 address within a particular scope can only communicate with addresses in that scope. So if you have your local scope address, you can only communicate with other machines that also have that local scope address in that same scope. You are not allowed to use a local address to communicate with a global address, for example. You cannot jump from one scope to another. If a node needs to communicate with a multiple scope, then you will have to assign multiple addresses. So if your machine is going to communicate local, you give it a local address scope. If it's going to communicate global, then you also give it a global address scope. This is a huge departure from what you're used to. So IP version 4 definitely is different in this regard. IP version 4 does not have scopes. However, we did have the ability to make reservations where we could reserve addresses for an IP version 4 node, which might be perceived as the same idea, but it's really a completely different concept. Let's talk about the first major scope type, which is called a unicast address scope. First off, there's a special address called the unspecified address. This is called : and it's on a /128. And this is basically all zeros, right? Because all the zeros are compressed. So basically, this is used when the node does not have an assigned address. The IP version 4 equivalent of this was 0.0.0.0. So that's what that address is. It's a special address. You also have the loopback. The loopback is 1, right? So all zeros compressed with a 1 at the end. And the IP version 4 equivalent was 127.0.0.1, often referred to as localhost. So in this case, the localhost or the loopback address for IPv6 is : 1. So once you learn how to ping with IPv6, you can ping that loopback address and get a response. And this allows you to test the functionality of TCP/IP on your local machine. Your machine can also be assigned a global unicast address. This is going to be varied. Every machine will have a different one. But the global unicast address begins with a global routing prefix that is fixed. Now, the IP version 4 equivalent for this was having public addresses like a Class A, Class B, Class C address. And so this is for general communication from node to node across the internet. And this is called what we call the global unicast. And this allows you to communicate globally. So the scope is global. There's also an IP version 4 transition address. Basically, what it does is it takes the entire IP version 4 address space and puts it inside an IPv6 address. And this was to transition from IPv4 to IPv6. Basically, you know you're dealing with an IPv4 transition address when you see it as compressed zeros, colon, colon, with 4 Fs followed by, and you'll see the IP address embedded in there. This is the IP version 4 transition address. You also have what was called link local addresses. Link local addresses are defined as a scope as only local. This is the API-PA equivalent. It's actually much better than API-PA. But remember, API-PA and IPv4 use the 169.254/16 network range. Link local uses FE80, colon, colon, followed by whatever number. And so FE80 is how you know you're dealing with a link local. This would be for machines that need to communicate locally, but don't need to communicate on a global scope. You also have what we just called unique local addresses. Unique local addresses are not routable, meaning they cannot be routed globally. They can be freely assigned by a network administrator on a local network. And in this case, it's followed by FC00, colon, colon. And this, don't confuse this with NAT. These unique local addresses cannot be NATed to a public address. That doesn't exist. Rather, these are local addresses that you want to be unique, you don't want to be duplicated, and they're non-routable. Multicast address scopes. There are predefined multicast address scopes based on the size of the scope, and you can create your own. You can create 8 custom multicast scopes, but beyond the custom ones, these are the following. There's 5 of them. You have what is called interface local, which is the node's own network interface. Link local, which is everybody that is local to you. Site local, which is a physical site which the node resides. Organization local, which is an autonomous system that machine is joined. And then there's global, which means everybody. And these are what we call multicast address scopes. So when I send a communication to a group of machines, I can choose to send it to one of those multicast scopes. Just out my interface, just to my local, just to my site, just to my organization, or globally. And then there's custom ones you can create as well. So let's take a look at some of the predefined multicast addresses. IPv6 has several predefined ones that replace IPv4 broadcasts. And so let's take a look at those. First off, you have the all nodes address. That's FF01, colon, colon, 1. This one is called interface local. And then you have FF02, colon, colon, 1, which is link local. So both of these communicate to local nodes. So if I wanted to send a multicast, or a broadcast, if you will, to all machines locally, I would send it to that address and it would achieve the same purpose as an old IPv4 broadcast. Then you have the all routers address, which will communicate with all routers. That one's FF012 and FF022. So that is the address for all routers to listen to. A lot of times we need to send router advertisements out, for example, and we want all routers to hear it. We also have the solicited node address, and that's FF02, colon, colon, 1, and then you can see the rest of the address there. This is specifically for IP version 6 discovering other IP version 6 machines. So this is used for neighbor discovery. So IPv6 hosts will naturally listen to this to participate in neighbor discovery solicitations. Speaking of which, let's do a deep dive into neighbor discovery and talk about what that is. Neighbor discovery is a process in IPv6 that manages communications among nodes on a local link. This is important for a lot of reasons. Let's talk about the 4 main functions that it serves. First off, it provides information about the network. What routers are available, what prefixes have been used, maximum transmission unit size, those things that a network node needs to know. it needs to also it's used to resolve the MAC addresses of neighboring nodes. Remember, we used to use ARP. Well, we don't use that anymore. We use what is called neighbor discovery. And neighbor discovery is what resolves the MAC. It does much more than just get the MAC, though. It does all these other things like discover machines, routers, gateways. All these things are handled by the neighbor discovery process. It also lets you know what nodes are reachable. I mean, why send a communication if the node is not up, right? It also provides a better redirection to another gateway. So let's say you're trying to communicate out and your gateway goes down. It'll redirect to a gateway that is available. So it serves these primary 4 functions, and these are all limitations of the IP version 4 protocol that have been improved upon in IPv6. Network discovery replaces the need for ARP. It replaces the need for what is called ICMP redirect and ICMP router discovery. So those 3 protocols are now gone and no longer required when using IPv6. Let's talk a little bit more about the mechanics of neighbor discovery. Neighbor discovery works by sending ICMP version 6 messages. So these are the ICMP protocol using the version 6 of that protocol. First off, network discovery sends out a router solicitation. Host machines will send out a solicitation asking if there are any routers on my local link, because you might need a router in order to communicate with another network. So I will send a solicitation out looking for routers on my local link. Second, router advertisement. Routers will send out router solicitations to find other routers and provide information about what prefixes are used, what maximum transmission unit is being used, what routes are available, and any auto configuration information that might be on that particular router. We also will redirect. So routers can send a neighbor discovery to redirect hosts to go to another or a better path than the one that they are on. So that is the purposes and the reasons behind network discovery. We can also do neighbor solicitation. So hosts can solicit each other with network discovery, and this is the replacement of what we used to know as ARP. So it'll go out and find out, hey, are you reachable? And if you are, tell me what your MAC is. And also, this is a great way for us to discover if there are duplicate IP version 6 addresses in our local scope. We can also use it as neighbor advertisement. Neighbor advertisement allows us to let us know that there are nodes available on the network to talk to. These are sent as a response to a solicitation. It provides information on whether the node is a host or it's a routing device, and it'll provide the MAC address of the node that is performing the neighbor advertisement. All right, let's now talk about another major feature of IPv6, which is the ability to do auto configuration. As you can imagine, manually assigning IP version 6 addresses could be a bit time consuming. So auto configuration is the process of automatically assigning a global unique address to an interface without somebody actually having to go to that machine to program it. IPv6 has 2 ways of doing this. First way is called stateful autoconfiguration, and the second way is called stateless autoconfiguration. An IP version 6 network can use either one or both at the same time, or neither. So you can choose to go with both, or just one, or none at all. So that's autoconfiguration. Let's talk about stateful. Stateful requires a central server. This is known as a DHCP version 6 server. So basically it tracks all of the hosts addresses given to hosts on an IP version 6 address. These are 2 things unique to DHCP version 6. Hosts identify them to DHCP version 6 servers with what is called a DHCP unique identifier, or DUID, rather than using their MAC address. There's a couple of reasons for this, but we don't need to talk about that too much. DHCP's 6 servers can assign entire prefixes to downstream routers via DHCP v6 prefix delegation. This really improves the ability for us to get more devices assigning addresses rather than one central device. So if we have a downstream router at a branch or wherever, we can notify that branch, hey, you've been given this prefix. I want you to assign out addresses for this prefix to that particular network, which makes management of DHCP so much easier. Pretty much DHCP, though, version 4 and DHCP version 6 operate effectively the same way. Let's talk about stateless. Stateless is a unique process in IPv6 which allows IPv6 nodes to generate their own globally unique address. This is done with what we call Stateless Address Autoconfiguration, or SLAAC. SLAAC relies entirely upon neighbor discovery protocol in order for this to function. They are generated from what is called EUI64, which is an industry standard. EUI64 addresses are there's a process for generating an address like this on your machine. We'll talk about it in a minute. It's not just your MAC address, so we need to talk about it. We will. So basically what happens is your EUI64 number is created by your machine, and then it uses that identifier to assign itself a global unique address. And so this is what the process of SLAAC is. But in order to really get this, we have to know what an EUI64 number is. This is a 64-bit number that identifies a particular address. For Ethernet interfaces, the EUI64 is derived from the MAC. It is not the MAC. It is simply derived from the MAC. So it is combined with the IPv6 prefix. Now, what happens is your host hears about, from routers, it hears what the available prefix is. It takes that prefix and it adds it to the EUI64 identifier it's generated, and that is what produces its self-identified address, or its SLAAC address. So how do you actually get from a MAC to an EUI64 to an IPv6 address? Let's go through this because it's rather complicated. First, you start with your MAC address. Then you take the MAC and you split it away from the OUI portion, which is the company assigned portion, and the MAC and the NIC portion. So you separate those two out, and basically you change the OUI from to 02. So you're actually changing the OUI to 02. The 02 lets us know this was an EUI64 generated address, by the way. Then we insert FFFE in between the OUI and the NIC portions, and that generates the EUI64 identifier. We then change the colons to IP version 6 by removing leading zeros or whatever we have to do, and then we add a prefix to it that is advertised by the router. Most routers will be advertising a /64 or a /48 prefix. In this case, just for example purposes, I showed the /64. So here's our advertised prefix, a 2001:DB8::/64. I'm now going to take that and I'm going to append my EUI64 to that IPv6 prefix, and now I have my SLAAC address. It'll almost always be the 64 block that gets advertised, and so you'll see 2001:DB8, and then your leading zeros, followed by your EUI64. Right? So that's how you get to the SLAAC address. Now, this is the process for how it works. Number one, a node that requires an address sends a router solicitation, which is an ICMP v6 packet, to all routers in the local link. One or more routers will respond back with a router advertisement. So it goes solicitation, advertisement. And basically it sends an advertisement out advertising what the prefix is for use on that network. For the prefix that are configured to use SLAAC, so some prefixes will be configured to use SLAAC. For the ones that are, the machine will take its EUI64, append it, automatically generate the IPv6 address, and append it, and it will then begin to use that address, and it will assign it to the appropriate interface. Now, some of you hackers have been thinking, if I have an EUI64 address that I know is derived from the MAC, I can take apart that number and I can figure out what the MAC is. Now, this is a privacy concern. Now, why is it a privacy concern? Well, think about it. If I know what the MAC address of your machine is, I can now know everywhere you go. Because IP version 6 is no longer NAT controlled, so everywhere you go, I can figure out where you've been. Whether your phone, it was your phone, for example. Your phone hit a wireless network at school. at a school. Your phone was on a cell tower. Your son was at a public hotspot. Your phone was on a public hotspot somewhere. Your phone was in your car. It was on a freeway. It was at an airport. I could be able to, by finding that MAC, query databases and find out everywhere your device had been because I simply knew what your MAC address was. So that could be a problem. So since SLAAC addresses are derived from a hardware address, now we can identify the manufacturer and the model of the NIC on that node, and that's also a privacy concern. So what we can do? Well, they implemented what is called privacy extensions for SLAAC. When privacy extensions are enabled, the node creates a SLAAC address by combining the IPv6 addresses with a randomly generated host identifier. A node with privacy extensions enabled will use the SLAAC address as the source address for new outbound connections. The EUI64 generated IPv6 address is still available for unsolicited inbound connections. So this is what we call privacy extensions. It uses a randomly generated host identifier. And so privacy extensions are available on most operating systems nowadays because when EUI64 first came out, everybody was panicking because they thought we would all be given an identifier that could track us wherever we went in the world. And so that's what privacy extensions are for. So how does a node know whether to use DHCP version 6 or SLAAC? You might have heard me mention it just a few minutes ago. If it is a SLAAC identified prefix, well, how do you know that? Well, we do that with router advertisement flags. So when we do a solicitation and a router advertisement comes back, we do a router advertisement flag. An IPv6 router sends a router advertisement in response to a solicitation from a node. The router advertisement contains one or more prefixes that it is using for that local link. The router advertisement also includes flags, and the flag will determine, is this a SLAAC, DHCP version 6, both or neither. And the flags are configured on the router. So in your router, you would have to configure what setting you would want to have, either SLAAC, DHCP version 6, both or not, or neither. So let's talk about the main router advertisement flags that are available. The two flags that will determine whether to use DHCP version 6 are the M flag and the O flag. The M flag stands for Managed Address Configuration, and that determines whether to use DHCP version 6 for IP configuration. The O flag means Other, determines whether to use DHCP version 6 for configuration of other options, such as DNS, network time servers, things like that. Each prefix that is being advertised also contains an A flag for Autonomous Address Configuration, which determines whether the node should be SLAAC or not. So you have M, you have O, and then you have A. So M and O refer to DHCP version 6. So if the M flag is on, it means use DHCP. If the O flag is on, it says not only use DHCP, but also use it for other options. If the A flag is on, it says also configure a SLAAC address. So here would be an example of the flags. So if we had no address automatic configuration, M, O, and A would all be zeros. If we wanted to have DHCP version 6 to assign the address only, then we would set M to 1. Almost always you have M to 1 and O to 1 at the same time because you also want your DNS server set and everything like that. So here's an example. The third example here is M, O, and A are all 1. This means DHCP version 6 is being used for everything, and we're also using SLAAC. So there you go. So these are all the different types of options you can do on flags for router advertisements. Now there are some caveats for auto configuration. Now auto configuration is going through a lot of changes. So this slide may be out of date very quickly, but this is the way it is out of the time of this writing of this PowerPoint. Not all devices support auto configuration. So general purpose operating systems will, but a lot of devices won't, like printers, cameras, phones. Many of them will not. Although a lot of mobile phones nowadays are. In fact, your mobile phone right now probably has an IP version 6 address. All devices support auto configuration via SLAAC, but most do not support using DNS versus SLAAC. Going back to my previous slide, you'll notice that you can have an M0, O1, and A1, meaning you'll use DHCP to get the DNS address, but you'll use auto configuration SLAAC to assign the address. This is a unique situation where you want to be assigned a DNS server, but you don't want to be assigned an IP address by the DHCP server. So in that case, SLAAC does support that, but not all devices will support that. So be careful if you try to implement that. Some devices will not support it. All right, now the dreaded subject, IP version 6 subnetting. Drum roll, please. All right, so IP version 6 subnetting, good news, is really easy. But it's just like IP version 6. It's just like IP version 4. Oftentimes, we need to subnet or break our address down into groups or into smaller segments in order to accommodate many organizations within our network. But subnetting IP version 6 is a lot easier. So let's go over it. One of the challenges of subnetting IPv4 is balancing the number of networks with the number of usable hosts. In IP version 6, it's really easy. All end user subnets have a subnet mask of /64. Done. End of story. Everybody has a /64 on an end user subnet. This makes it really easy. Everybody is going to get the same size of network. We don't concern ourselves with the number of hosts. There are smaller subnets for loopbacks, point-to-point links like between router devices, but these are specialty circumstances. They would not be assigned to hosts. Smaller subnets are not supported in general, meaning if you use smaller subnets in a /64, it will break SLAAC. It'll also break some other router advertisement issues, so be very careful when trying to create smaller subnets, even if you want to. The only relevant number, the only thing you need to know when calculating an IP version 6 subnet is the number of subnets you need. Never worry about the number of hosts. Unless, of course, you have this gigantic intergalactic network that takes billions of hosts, but I don't think you do. Okay, IP version 6 network should always be subnetted in a hierarchical fashion. So you want route summarization to be used. If you remember IPv4, we had a way to summarize multiple routes into one address. We do the same thing in IPv6. So make sure that when you pick an address, use the next one and the next one. Don't jump all throughout your range if you can avoid it. IPv6 networks should be subnetted such that the subnet mask is divisible by 4. Why? Well, this is kind of an interesting idea. Because we're using hexadecimal, we want the number to be divisible by 4 so we can represent it with a hexadecimal 4. Remember, each block in an IPv6 has 4 hexadecimal digits. So we want to be able to represent the subnet easily with that hexadecimal block. So we do not want our range to end in the middle of a hex range. We want it to end on a divisible of 4. So a divisor of 4. So always make sure that your subnet mask is divisible by 4. And then you'll know you're good. And by the way, all subnets that you want to assign to end users must have a /64 subnet mask. Here's a great example. You're a junior network administrator for the finance department for Global Megacorp. A senior administrator has assigned your department an IPv6 address of 2001:dead:12/56. Now, you may be wondering, dead beef? Yep, that is a legitimate address. Notice, D is a valid hex address, E is valid hex, A is valid hex, D is valid hex, right? All those are valid hex numbers. So I know that sounds funny, but that's the way. I just wanted to make sure you understood that. So we started with /56. So we want to subnet this /56. So you need to provide addresses for 9 VLANs. The number of hosts can vary from 40 to 1,000. How will we do this in IPv6? So first off, the number of hosts do not matter. Just focus on the number of VLANs. So we want to take a /56, and we're going to take the /56 and extend it to a /64, right? That'll give us 256. So how many bits are different between a /56 and a /64? That's 8, right? So 2 to the power of 8 is 256. So by extending from a /56 to a /64, we have created 256 individual prefixes. You can now subnet those directly to 256 prefixes, or you can subnet them into a whole bunch of /60s and then subnet them into a bunch of /64s if you want to. Either one will work. I've decided to go from a /56 straight to a /64. I could have went to a /56 to a /60 and then taken each one of those /60s and broke them down into /56s. Either one would work. Let's go with the first one. All right, so that's how you do your subnetting. Pretty easy. IP version 6 and DNS. IP version 6 and DNS. DNS has been extended to support IPv6. You now have a record inside DNS called Quad A or AAAA. We always say Quad A. A Quad A resource record has been added to support IPv6 host names. The pointer resource record has also been updated. Pointer is for the reverse lookup from IP to name, not named IP. You have other record types have not changed. MX, CNAME, NS, those have not changed. But MX, CNAME, A records, all those things, they all support both A and Quad A host names. The Quad A resource record has been added to support host names, and they work exactly the same way that A records did in IP version 4. You basically request, hey, I'd like to know what the IP address is for this DNS host name, and the DNS server replies back with the address. Pointer records stay as is, but a new format's been created for IPv6. IPv6 used the root domain ip6.arpa. You'll remember IP version 4 had their own root domain, and it still does. IPv6 addresses are represented as individual nibbles, that's what they call them, which is a single hex digit. So every block has 4 nibbles in it. And these are separated by dots and reversed sequentially in order for you to resolve backwards from IP to DNS. They do not use zero compression when you use these as well, by the way. So here's a pointer example. Let's say google.com resolves to the following IP address. Let's expand that out to its full IPv6 address. We're going to reverse the digits, and we're going to put a dot in between each nibble. Do you see how that works? Then that is going to be appended to the ip6.arpa pointer record. This gives us the ability, whenever somebody wants to know what the name is for a given IP, I can look at my pointer record and know what the name was. And that's how the IPv6 pointer work. IPv6 addresses are very long and difficult to remember, so it's a very good idea to use DNS and host names with IPv6. People are just not going to remember your IPv6 address. IPv6 addresses will never change, or hardly ever, unless you're using a SLAAC address that's using a privacy address. Very rarely will an IPv6 address, because we have so many addresses, a machine will just always keep the same IPv6 address. So we don't have to worry about dynamic DNS and things like that as much. And also, another important point, a DNS server does not need to be an IPv6 host in order for it to have IPv6 resource records. So that's an important consideration. So you can support IPv6 without your DNS server actually having IPv6 on it. All right, last but not least, let's go over in Microsoft Windows, what are some command line tools you can use to test out IPv6. First off, Windows Vista and Greater all support IPv6. So IPv6 is supported. Windows XP and 2003 Server support IPv6, but you have to add it. And when you add it, you don't get DHCP-v6. You don't get DNS lookups. It must be configured via the command line. There's no way to program it in there manually with a graphical interface. And a lot of the services in Windows 2003 and XP will not recognize IPv6. So everything I'm going to talk about here assumes that we're using Windows Vista and Greater. By the way, router discovery is also not available in Windows XP as well. So here's your IPv6 IPCONFIG. So if you have an IP version 6 address and you type IPCONFIG at the command prompt, so you will get an output that looks like this. The IPCONFIG will show your IPv6 address, It'll also show your IP version 4 address if you have one. Notice in this case, I have a temporary address, I have a link local address, I have a global address. So notice I have multiple addresses automatically assigned by IPv6. So notice the particular one right here at the top was obtained by a DHCP version 6 server. The reason why I know that is because it's preferred. It got it through the auto configuration, and it came from DHCP version 6. It is a global address. And you can tell when the lease was obtained and when the lease is expired. The next one is a temporary address. This was assigned by SLAAC. SLAAC used a EUI64 address, and so this one was assigned by SLAAC. The next one is the link local IP version 6 address. This one is it does not follow EUI64. It's just a link local address assigned. Notice it contains at the end a %11. This is Windows' method to track a zone. So Windows has routing zones in it for its firewall and stuff. So it knows that this is zone for 11, which is probably the local zone, right? You also can see what your default gateway is. You also saw in your IPv6 address what your DUID was, your DHCP unique identifier. And so that was in there. And you can also see what your DNS server was that was assigned. The next command is called ping. In order to ping a host via an IPv6, you have to type ping space -6, and then you can ping the IP address. And so that's how you can ping it with IPv6. Okay. The next command is called traceroute. If you do traceroute -6, you can trace it using IPv6. Now, you can only do these commands if you're actually on an IPv6 network. You can actually get on an IPv6 network actually very easily by registering for and getting your own IP version 6 address at Hurricane Electric or some IPv6 provider like that. Another command is called pathping. Pathping will figure out your path is, and if it follows an IPv6 path, it'll tell you. The IP version 4 path ping would be the same. NSLOOKUP. When you type NSLOOKUP, you can type NSLOOKUP space -type equals quad A, right? And then the domain. And then the domain will reply back, the server will reply back with the IPv6 address rather than the IP version 4 address. You can also look up a pointer record. If you know what the IP address is, you can you can reverse it and look it up that way. In this case, in this example, we did a pointer record looking for this particular address, and we got back Wikipedia. The next command is netsh. Netsh allows you to see if there's any neighbor cache, stuff like that. When I type netsh interface IPv6 show neighbors, this shows me all of my IPv6 machines that were discovered via the IPv6 neighbor discovery process. Next command is route. You can type route print -6. This will show you your IP version 6 routing table. And that's basically it. So we have gone over the entire IP version 6 address space. I've covered all the basic ideas: auto configuration, neighbor discovery, address format, how addresses are created. So hopefully you got a pretty good picture of what an IP version 6 address is now. Thank you very much.